calculus. I know. All right. We're good? It was just, sorry, Molly was taking a picture. I just want to make sure I wasn't moving on. All good. Okay. We can do it. It's fine. So there's like a lot of words, you know. We'll go through it, but what? We are going to connect the graph of the derivative and the second derivative with our original graph. So we haven't done any second derivatives in application, and that's what we're going to do today. This is the same picture that we had before, right? So where do we have maximums and minimums? At like, what? Horizontal tangents, or also where the derivative is undefined, right? Also could occur at our endpoints, right? Which we saw in the homework.
Yeah.
Okay. So we've kind of already done half of this lesson. So when you think it's a long lesson, you'll see I already introduced you to a lot of this material and these skills in previous lesson. So this is an actual theorem. We don't really call it a theorem. It's just how we find local extrema. Oh, that's supposed to say 5.1, by the way. That's all right. There we go. So when we have a critical point, which I understand some of us are still kind of confused about how we find those critical points, we'll have more practice today. So again, critical points are where the derivative is equal to 0 or where it's undefined, okay? Now, where it changes from positive to negative, that's a local maximum. We've already done that. We've done that. Remember where we did increasing and decreasing? We did like the arrows and the plus minus. So if it goes from positive to negative, we have a maximum. And then if it changes from negative to positive, we got a local minimum, right? If it doesn't change sign, then it has no local extreme at C. So remember this example I was showing you on the homework, like f of x equals x cubed? It has a critical point, but it just increased and increased, so there's no minimum or maximum here. Okay. So again, this first example is going to look familiar. It's going to look like what we did for local extreme. First step, find. Okay, so yeah, we could do the domain. Thank you for reminding me. I do always want to think domain. This is a parabola, or sorry, not a parabola, a polynomial. So domain's all reals. Then we want to find the derivative. Okay, 3x squared minus 12. So I'm going to just factor it. So if we factor out the 3, it'll be x squared minus 4. So x plus 2. Good. Okay, what are my critical points? -2 and +2. Are there any places where the derivative's undefined?
No.
No, it's just a polynomial. So that we just have to worry about setting it equal to 0. Yes?
Isn't it since it's an x cubed graph and it's like at 0, it's something it's different?
So x cubed could have maximum and minimums. With an x cubed function, you could either have two max or min, or a max and a min, or no max or mins. You'll see. Like, let's put the number line together. Okay, I'm going to label that f prime. I don't have any endpoints, so I'm just going to put -infinity to infinity. And I have 2 critical points. So I'm going to put -2, +2. So I have 3 intervals that I want to consider. Okay. There's a reason why I like to have the derivative in the factored form. It just makes it a lot easier. I mean, you can plug it into here as well. But here, if I have a -3, so it'll be negative times negative, which is positive, the 3 in front, so positive. Plug in 0, I get positive times negative, so negative. Plug in something bigger than 2, positive, positive. So it goes up, then it goes down, then it goes up. Okay, again, I like to introduce these methods earlier on, so when we get to this point, it just kind of flows a little more smoothly. So we have a max and a min. So my maximum is going to be f of negative 2.
You have to write local,
Yeah, it's fine. If you just write max and min, I'm fine with that.
but then you would write absolute.
If I want absolute, I'll specify.
Okay.
Yeah.
Wait,
Especially on the quizzes and the tests, I will ask you for the absolute max and the absolute min. Otherwise, if I don't specify, then just say max or min. Okay, it's really fine. Okay, so what do we do when we're actually finding the maximum and the minimum values? Right? Again, that's why I like this notation. It reminds us what we're plugging into versus here we were plugging into the derivative. So plug in negative 2. So negative 8 plus 24. 16 minus 5. Yes. And plug in 2. We got 8 minus negative 20. Negative 21. Yes. We can do some mental math, even though it's last period. Good? Don't worry about the support your answers graphically for now. Just know you can graph this on your calculator, right? Are we able to see where the max and min are on our calculator? Of course. Okay, got another one. Okay, x squared minus 3 times e to the x. I can multiply this out and then do the derivative, or we can just do product rule. Before we do that, let's just mention our domain. Is there anything I can't plug in? No, so it's just going to be negative infinity to infinity. Okay, so we'll make it x squared minus 3 will be our u, so 2x e to the x plus x squared minus 3. Derivative of e to the x is e to the x. Now, I would like you, in the past, I would say don't multiply this out, right? If I was just asking you to find the derivative. But because we want to try to find where it's equal to 0, I do want you to factor. What can we factor out of each term? E to the x. And I'm left with 2x plus x squared minus 3. Or x squared plus 2x minus 3. Does that factor? It's going to be plus 3 minus 1. So again, before we try to set it equal to 0, just try to get it in that factored form. And now it's really easy to see. What are our critical points? Negative 3 and 1. E to the x will never be equal to 0, right? So we're going to exclude that one. So setting it equal to 0. So our critical points are negative 3 and 1. Good? Okay. I'm going to make a number line, leave some space above. Make sure to label it f prime so we remember that's what we're plugging into. We got negative infinity, positive infinity, and negative 3 and 1. Again, what's really nice about having the factored form, it's easy to substitute in. Don't try to plug it into this one. That's a mess. So if I have negative 4, e to the x is always positive, so I don't really have to think about that one. So negative 4, so I'll have a negative times negative, positive. Plug in 0, positive times negative, and plug in something bigger than 1, positive times positive. So it goes up, down, up. Yeah.
Would they ever be like the same when I do it, like positive, negative, negative? Like, will that happen?
Yes. Yeah.
I think we haven't seen that.
It could go positive, negative, negative. The way that might occur is an example of that would be, let's say you get a derivative and it's like x squared, x minus 3 to the third power. Just throwing that out. Remember something you talked about in pre-calc called multiplicity? Okay, what happens when it's even multiplicity? It's going to bounce off the axis, okay, and it's not going to cross. Yeah, and then if it's odd, it's going to go through. So an example of this one, at 0, it's not going to change sign.
But there would go like,
Yeah, so look at these. If I think back to this one that we just did, I have powers of 1 and 1. I know it's going to cross. So that's a good way to just look back at our derivative and say, is it going to change sign? I knew before I even did the number line it was going to change sign because these are odd multiplicities.
We can use multiplicity.
Yeah, absolutely. I mean, we want to figure out which one. So we want to make sure. I usually plug it into all of them just to make sure. But if I end up with a positive, negative, negative in this situation, I know I did something wrong because that can't happen. Unless, of course, if the x minus 1 had a power of 2, then that would make sense. Good?
But then what would that mean for your like minimums and maximums? You have two arrows going down, right?
You just wouldn't have a minimum then. You would just have a maximum, which could occur. Okay.
Question.
Yeah.
So do you only have like a minimum or a maximum at the end when it's closed in brackets? So
Oh, yes. Good question. If I gave you a domain that had a closed interval, so let's say this was like -7, that means you would also have a minimum at -7. And let's say this was like 3, you would also have a maximum at 3.
Okay.
But because the domain is -infinity to infinity, we don't worry about that. Okay, if we plug in -3, so that'll be 9 minus 3, 6, e to the -3. Just 6 over e cubed, it's fine. And then the min, f of 1. So that'll be -2 e to the first. Right? So -2 e. How was that? Okay? You're going to say, I know what you're already thinking. You're like, this was okay, but then I do the problems on the homework.
these are always
I know.
These are easier. They're just like factually easier.
Okay. Okay. I hear what you're saying. Maybe I like to, maybe I make you work for it a little bit at home. I don't know. All right. Also, it's easier when we work them out together. Yeah. Okay. Concavity. So, what is concavity? Okay. Like concave, convex, concave up, concave down.
Yeah.
Geometry?
Geometry, we did concave.
That was
We did it last year.
convex.
So we did concave. So convex are the polygons that we usually work with. Concave is when it like goes inward at some point. All right.
Oh, yeah.
This is a little different. Okay. We're only going to refer to concave up and concave down. All right. Basically, concavity has to do with the second derivative. So what it's saying, and I know this picture's a little complicated looking, but say you have your tangents. What's happening to the tangent as I get closer? So it starts out steeper and then it starts, right. So what's happening here, my derivatives are getting smaller and smaller. Okay, so if y prime is getting smaller and smaller, it's going to be concave down. You see how the tangent slopes, as I follow the line, the tangent slope is getting less steep. Okay, versus over here on this side, what's happening if I follow my tangent line? What's happening? It's getting steeper and steeper. So when it's y prime is increasing, it's concave up. When y prime is decreasing, it's concave down. Okay, and just kind of picture, do you see this part of the graph here? It's concave down. So almost think of like an upside down parabola is concave down on its domain versus a parabola that's facing upward, right? That's going to be concave up. Okay, so let me just go back here. If it says y prime is increasing, that's talking about the derivative of the derivative is positive. Okay, if it says it's increasing, we're talking about the rate of this. So I'm basically, I'm talking about the instantaneous rate of y prime, which would be the second derivative. So here we go. Concave up, y prime has to be greater than 0.
So it's like the slope of the slope?
It's the slope of the slope.
So it's the acceleration.
Exactly. It's like acceleration.
But how is that? Y prime is not like the second.
It's the second derivative.
Y double prime.
So when this says y prime is increasing, this is saying the rate of y prime is positive. That's another way to describe it. So if I'm saying the rate of y prime, I'm doing the derivative of the derivative, or in other words, the second derivative. Okay? Do you see the connection there? If not, just remember second derivative has to be positive for it to be concave up. And then concave down is when it's less than 0. One thing I want to just highlight here, it must be twice differentiable. Remember mean value theorem? I said it had to be continuous on a closed interval and differentiable. This one, you can't find concavity unless you are able to take the derivative twice. Otherwise, it's not, the second derivative isn't defined. Most of the time it will. Okay, I'm not going to give you like crazy examples. Yeah, so like take this example. We have a to the 4th power. That's a polynomial. So can you find the first and the second derivative? Yes. So let's go. First, we got to find the first derivative. So we have negative 4x cubed plus 12x squared minus 4. Okay. Don't do anything to the first derivative. Don't try to factor anything out. Just keep going. So second derivative is good, negative 12x squared.
24x. Now take out.
Now I'm going to factor. Good. So what can we factor out? Negative 12x, or negative, it doesn't really matter. So then I'll just get x minus 2. Okay, now these are technically not critical points, but what I want to do is I'm going to do the same thing that we did with the first derivative when we were doing maximum and minimums, increasing and decreasing. I want to find out where the second derivative is equal to 0, and then we're going to do a number line with that. So I get x equals 0 and 2. Okay, leave some space above, just like we did with the other number lines. I'm going to label this one y double prime. Okay, good so far? So the domain for this one, yeah, we can put domain here. That's fine. Yeah, negative infinity to infinity because it's just a polynomial. Okay, so I put 0 and I put 2. Now, we don't really have to worry about the domain in this case, but just keep in mind if you have any places where the function's undefined, we want to put like open circles for those or not include them. You got a question, Ryan?
Yeah, for x equals 0 and 2, you said they're not CP points, right?
They're not, I don't call them critical points, are exclusive to first derivative. Yeah, so critical points are actually a thing. Like if you talk to someone else who's taking calculus and you talk about critical points, it's only when the first derivative is equal to 0 or undefined. Second derivative, we just use those values where it's equal to 0 to set up our number line. Okay.
So they're just not important.
I mean, maybe we want to call them like crucial points. I don't know. Okay, let's check something like -1. So this will be positive times negative. So we get a negative. Oh, second derivative. Okay. Whenever you're not sure, look at how we labeled the number line. That will tell us what we're always plugging back into. Okay, so, and I like to do the one that's factored, right? So plug in, let's say, positive 1. So that's going to be negative times negative, positive. And then something bigger than 2 is going to be negative, positive, so negative. Okay, I'm not going to put arrows. I'm going to put little parabolas above. Okay, remember what I said about concave down? We think of an upside down parabola.
Okay.
And then up. And then sad face. Okay, so where is it concave up? 0 to 2. One of the things I should always say, always use parentheses for concavity. You can't include the endpoints here because it doesn't make sense for it to be concave up or down at a point. Okay, so we're going to say from 0 to 2, and it's going to be concave down from negative infinity to 0 union 2 to infinity.
That's what that U means?
Union? Yeah, union. You guys
What? Union? I can't believe.
Yes,
I'm in shock. Like, what?
it's a union. Yes,
What? Union of the union, right? Wait, what?
union.
What? So what does it stand for?
I thought it was like.
Unification.
I thought it was just like a Greek letter or something like that.
It's like this. Like,
Yeah.
Union.
Oh.
It's the union.
That's crazy.
And then this is
Oh,
the,
now
that's the
that
intersection
all
now.
makes sense.
I've never seen that.
Yeah, we know
Okay.
Wait, what?
No.
The upside down one is the intersection. This is the union. Union means or, basically. Union. So it means
You don't need it.
x is less than 0 or x is greater than 2. That's the translation into interval
She
notation.
was just
So
told.
Lincoln was like speaking.
No, she was
in
just
her
like, just put a U. Just
Yeah, she
I was like, okay.
said union.
That's how I knew it.
She did. She definitely did say
Okay,
union.
okay. All right. This one we were given a domain, so just keep that in mind. Although the endpoints aren't included, which is fine. We're just looking from 0 to 2 pi. So the derivative of 3 plus sine x is just going to be cosine x. Second derivative is negative sine x. Okay, we want to find the not critical points, maybe crucial points. And we're looking specifically on the unit circle, but we're not including 0 and 2 pi, which means there's only one place that could be equal to 0, pi. Okay, think about the unit circle, right? Right, this is 0 and
Well, who cares?
oh, okay, same thing, right?
It's fine.
Okay, right? But we're not including the 0 and the 2 pi, so we just have here. Okay. Oh, we can divide by -1 on both sides, and we still just get 0 equals sine of x, and that will... Sorry, I just kind of ignored the coefficient.
It's pi to get sine to be.
Okay,
Oh, and you can't use 2 pi because there's no bracket.
exactly,
bracket, you could.
exactly.
Okay.
If there was a bracket, we would include it.
Got it.
So, here we go. How did I label my number line? With the second derivative. That's what we're testing into. Okay, here's my... You don't have to. I just like to do it because it's easier for me when I try to, like when I write it all out in interval notation. Okay, negative sine. So let's see. Pi over 2. Sine of pi over 2 is 1, but then there will be a negative in front, so -1.
Yeah.
So that will be concave down. Has to be +1 because it would be 3 pi over 2 will give us -1, -1. Give us positive. Also, just think about this graph, 3 plus sine x. We know what that looks like, right? It's just a, we know what sine x looks like, right? Doesn't it make sense that it's concave? Doesn't that look like a sine curve?
Oh.
Wait, is that going up?
Yeah, it moves it up.
Oh yeah.
So does it actually change where the concavity is? Not at all.
No.
So concave up and concave down. So where is it going to be concave up? From pi to 2 pi, and concave down. 0. He's
I
shushing.
know, right? That's what I was thinking.
Whew. All right, you got this all, Ryan? Again, okay, the next part is an extension of what we just did, okay?
I believe.
I promise. I promise you. Do you see all these places where it changed concavity?
Yeah.
Okay, that has a name, and it's called point of inflection. So the point of inflection,
Looks too much like infection.
have we heard inflection? Like an inflection point, right, with voice or whatever?
No.
You've never heard of,
Inflection points?
no. Okay, well,
Never heard of that.
now I'm introducing you to the term inflection.
And
So inflection is just where it changes concavity. That's all you need to know. Okay, so basically where the second derivative changes from positive to negative or negative to positive. So basically these last two examples was pretty much all the work we needed. The only thing that we would have done to find the point of inflection is figure out what f of pi was.
So it's,
Okay.
it's like the
So you go back to the original equation because you want the point on the original graph. Yeah. That's it. Okay. And there's steps here, but we kind of,
X equals, like you would say point.
we would say,
inflection X.
we would say f of pi equals 3. That's all. Just like how we do the max and the mins. Okay, here we go. Y prime. So here I'll follow the steps as we go through. So find y prime, double prime, and all the values where y double prime is 0 or undefined. Again, I put this little thing here. Make sure the points are in the domain. In this case, the domain is all reals again. So, okay, y prime. So we have to apply the chain rule, right? E to the negative x squared
Times negative 2.
negative 2x. Okay, second derivative.
We do product.
Yeah, product rule is fine, but we're gonna have to do that chain rule within the product rule. Well, the derivative of this is just what I have here, right?
Yeah. So let's rewrite
Oh, yeah.
that
Times e
negative 2x
times negative 2x.
plus
Good. Now it's
e to the negative x times negative 2.
good. Okay, before we set that equal to 0, I want to clean it up a little bit and see if there's any way we can factor it. Let's maybe multiply it out first. Let's make this a 4x squared
Got like a full like 2e.
minus 2e to the negative x squared. Yeah, what can we take out?
Take out the 2e to the negative x.
2e to the negative x squared. And I'm left with 2x squared minus 1. Okay.
Yeah.
Set that equal to 0. Now that 2e to the negative x squared,
0.
can that be equal to 0?
Oh, no.
No, it's an exponential function. So we really just have to set 2x squared minus 1 equal to 0. Sorry, I'm running out of room here. So it would be 1 over, right, divide by, so it's basically plus or minus square root of half.
So can we say 1?
Okay. Okay, so,
Oh, wait.
Isn't it 1 over root 2?
sure,
Is that easier?
Why did it?
doesn't matter. Why don't I? Because that's an exponential function, and it'll never be equal to 0.
They go like
Remember the exponential functions have a horizontal asymptote, so I don't bother with it. Okay, so I have negative infinity to infinity, and this is my second derivative. Negative 1 over root 2, positive 1 over root 2. Now, it looks complicated to try to plug in, but I promise, like, just pick some easy numbers. What are we plugging into? Second derivative. This whole 2e to the negative x squared is always positive. So always positive. I don't really care about plugging into that part. Make sense? So I'm just going to plug into this part. Right? What happens if I plug in, I don't know, negative 2, right? We're going to get positive. Something in between those, easy, 0, get negative. And then obviously to the right, we'll get positive. So it's going to go concave up, concave down, concave up. Now I'm not asking for concavity. There's 2 points of inflection. Okay, so I have f of negative 1 over root 2 and f of positive 1 over root 2. Again, it looks much more complicated than it.
No.
You'll tell me. You'll tell me?
Yes.
Okay. All right. Okay, plug it into the original function. Sorry, pointed to the wrong thing. So negative 1 over root 2. If I square that, that's just 1/2. So it's e to the negative 1/2. Good? Or, I mean, if you really want, you could do 1 over root e. I don't care.
It's fine if there's a negative exponent.
Did I usually like you to make it positive, but I'm just trying to save some time. Okay, and then what happens if I plug in positive?
Then just e to the 1.
Well, it's still negative, right? Isn't it the same thing?
You plug it back, it's like the original.
Oh, yes. I said f of, you could put y, whatever. When I'm actually finding the points of inflection, I'm going back to the original. Remember when we did maximum and minimum? Where do we get the actual points? It's from the original graph. So plug that in and we get the same answer. Right, because the negative is in front of the x squared. Right.
Interesting.
Okay.
Why is
Wait, when
why
the
is it
negative
So they
same?
change it the same x value?
No, it's different x values.
So we have different x values, but it has the same y value. That's okay. It just, this has symmetry. That's how we know. Okay, we could, again, you can graph it on your calculator and you can see it. Okay. This one, I know.
Yeah, we're not 5.4. The homework?
Okay. This one's easy. This is a parabola. So first thing I did was I just decided to multiply it out because I think it's easier to work with. First derivative is 12x squared minus 4x cubed. Double 24x minus 12x squared.
Wait, can you distribute for?
Yeah, that's what I did. I distributed.
So not like use the power rule.
Didn't we just
You
do
could
this?
do the product rule, but
Product rule.
yeah.
Wait, so we just get
So 12x and then 2 minus x.
0 and x equals
Good. So x equals 0 and 2. Oh, I didn't say the domain, but we see that it's all reals. Of course. Okay, again, I like to use the factored form, but it doesn't really matter. If I plug in negative 1, negative times positive, negative. Plug in positive 1, positive times positive. Again, look at that multiplicity. Aren't these both to the first power? So it better change sign. If it doesn't, then we made a mistake. So we got sad face, happy, sad. Okay, so what are our points of inflection? Okay, so f of 0 equals, that's easy to plug into, 0. And f of 2, so 8 times 2? 16. See? Okay, this is something that you could have done if you knew what the terminology meant. You could have done this in Algebra 2, basically. Okay, so what I want you to do, use the graph of the function. So this is the original function to estimate where f prime, f double prime are 0, positive, and negative. Okay. When is f prime equal to 0?
The slopes where it's
Yeah.
Okay. What does f prime equal to 0 mean? It has a horizontal tangent. So that's going to be when x equals, where does it have horizontal tangents? Here and here. When x equals 0 and 2. Okay.
Why don't we say like the y?
Oh, we're just checking for where it changes.
Yes. Okay, see the word where? I only want x values when I ask for where. I don't care about the y values. I know. It's a thing. Where, oh, sorry, I didn't mean to write that. Where is f prime greater than 0? Okay.
Any points that are
Where the slope is
Greater than 0.
positive.
Right.
So from negative infinity to,
0, and then from 2 to, right?
good. Sorry, I didn't leave you guys a lot of room here. And then where is this derivative less than 0? That's,
These are all just for part A?
yeah, and then we'll do the second derivative.
less than 0 between 0 and 2.
Yeah, 0 to 2. Okay, now for, does that make sense? So we're just looking at the graph and we're just interpreting increasing, decreasing. Okay, now let's do, where is the second derivative equal to 0? Okay, basically, look at where your max and your mins are. And pick right in the middle. Again, you can estimate. It says estimate here. Right where it switches, if you kind of take the midpoint of your max and your min, that's going to be a good estimate for your point of inflection. So here it's concave down, and then it switches to concave up.
But it's
Jeez.
not, it isn't like exactly always the point.
It's not going to be always exactly. It's just a way to estimate.
Okay.
So that's going to be when x equals 1. Sorry, I'm going to write this down here. Where is the derivative, the second derivative greater than 0? So now we're saying, where is it concave up? Well, we're going to start from 1 to infinity. Are we okay?
How is this like approaching it as a second derivative?
So I'm looking where it's concave up.
At the same thing.
I'm looking at the concavity. The x values are always going to stay consistent between the original graph, the derivative, and the second derivative. So now where is the second derivative less than 0? From negative infinity to 1. Right?
I mean, if we just look at whatever.
Yeah,
We take the midpoint of the max.
exactly. Oh. Looks like we're not going to finish. It's okay.
Oh no.
It's okay.
Yeah, yeah.
So tomorrow is a review day, but you have a take-home quiz. So if we need to take half the class to finish the lesson, and then we'll review,
So is there any problems that
No, wait, how are we gonna do
can't
homework?
do?
you'll be able to do almost every single thing. Because we basically, the only thing that I didn't get to yet, this local, I didn't get to there's another theorem, but all of the stuff on here, you could do everything except for D, because we've already done all the increasing, decreasing.
Wait, is it gonna be like calculator okay on like the quiz that we take